Hey everybody, this is Mr. Warner. We're doing 2.1 today. We have this great starter for 2.1. I'd maybe encourage you, if you'd like, to kind of go through this process, answer the questions. If you need any help, I have this filled in on the notes. But I think it's helpful to get into what we're covering today. I just don't want to add it to the video that we're covering today. So if you have any questions, please stop by. I'd love to talk to you about it. Okay? All right, so let's get into the notes for 2.1. So we're talking about polynomial properties. We're going to do 2 days of this. Today is going to be a little heavy, and then when we get to 2.2, we'll add a couple more things to that, and it shouldn't be as bad. Okay? So I kind of have some of this already written in just to save some time. So this is a polynomial where like a, if I can circle these, so like a and a sub 2 and a sub 1 and a sub 0, those are just the coefficients. And we have multiple terms here. Again, a term is typically a combination of numbers and variables. You could also have a constant at the end. These are just some things, this vocab that we'll be using. First off, is probably the most important for today, is what's called the leading term. So the leading term includes the degree, so the highest exponent of the polynomial. It's going to tell us some of the information that we need. And also we have the leading coefficient. That's also going to help us determine some of the behaviors of the polynomial. Okay? And then all the lower terms, while those are important, they're not as important when we talk about the big picture of the polynomial. All right, the constant, we'll get into that a little bit more next time, but it also, that gives us the y-intercept. So if you were to set y equals to, or sorry, x in for 0, then all of the terms would cancel out except for the constant, and that's why we end up getting the y-intercept is the x is 0, the y is going to be the constant at the end. Okay, so keep that in mind as we go along. Okay, all right, so we're going to be talking about a few of these theorems and properties that will help us come up with the information that we want to know from these polynomials. Okay, so first off is the fundamental theorem of algebra. Basically, the fundamental theorem of algebra, or what it gives us from the fundamental theorem of algebra, is how to know how many solutions a polynomial can have. Okay, so if polynomial, or if p of x is a polynomial of degree n greater than or equal to 1, so whatever n is, okay, then the p of x is equal to 0 has, so basically if we set the equation equal to 0, then we're going to have exactly n roots. Okay, these roots could be real, they could be complex. So if we look at this example, we can look at all of the terms and we could find the highest exponent. Again, that's your degree. So the degree will tell us the number of roots or solutions. So we would have 9 roots or 9 solutions, okay? 9 different things that could make this polynomial be equal to 0, okay? If we had another example, we could have something as simple as, I don't know, 2x to the 2 equal to 0. Well, here we would have 2 solutions, okay? Sometimes they are multiple. They could have like 2 solutions that are the same. Okay, I think that's what would happen here. Okay, but you will still have 2 solutions that could make this be equal to 0. Okay, I don't know if that was a great example, but I think hopefully that helps. All right, zero product property. We used this a lot last year when we were solving by factoring. We did it a little bit in our review for our first unit. So if you are multiplying 2 things and it's equal to 0, then either A or B, those 2 things, have to be 0 to make the equation be true. Okay, so here is more like what you would see after we factor. We want to know what would be the solutions at this point. Okay, so again, if two things, this is two things, here's 1, here's 2, if they're being multiplied and it's equal to 0, then we know that either x minus 2 has got to be equal to 0, or 4x plus 3 would have to be equal to 0. And we can solve those individually. We have to add, let's add 2, and we'd get x equals 2, would be one of our solutions, or our roots. And we could do the same thing here. We could subtract 3. And then we'd have to also divide by 4. So this would be our other solution. Okay? So our roots would be 2 and negative 3/4. Okay? You could have an example that had like x minus 2, and we'll get to stuff that looks like this really soon, where you have multiple terms, or multiple factors, so more than 2. You could even have ones that have like exponents on those parentheses, but still we're setting each of these individually to equal to 0 and solve. Okay, so for this example, we would end up getting 2, that negative 3/4, and would also get 7. So we'd have two solutions there. Okay? All right, next off, I know this is a lot of things, so you might need to go back to this as we go to the problems, but let's talk about multiplicity. So multiplicity, if we kind of go back, and we didn't really go into this a whole lot, okay, but when we have this example, when we factor, we end up getting two solutions that are the same. So maybe going from this point, if we set each of those equal to 0, we end up getting x equals 1 and 1, okay? So this is called multiplicity, meaning we have multiple roots that are the same. So if there's more than one of the same type of root, then we'll say, for this example, we have two things, so we would call it a multiplicity of 2, okay? So if we kind of go back to where we were here, okay, we can come up with our zeros. Again, we can set each of these equal to 0. So if we set that equal to 0, we'd get negative 1. If we set this equal to 0 and solve, we'd get 2. And if we set this equal to 0 and we solve, we would get x equals 6. Okay? But think of it about like this. This term, or this factor, is being multiplied by itself 3 times. So we would end up getting 3 solutions from this factor. They're all the same. We'd get 6 and 6 and another 6. Okay? And if you have, like I said, if we have multiple things, then we would get a multiplicity of 3. So you can see this easily by just looking at the exponents. So maybe I'll write this above. So this would be a multiplicity, I'm going to shorten that, multiplicity of 3. This would be a multiplicity of 2. And this would be a multiplicity of 1. Okay? If it's a 1, I think oftentimes we don't maybe write that out, but your homework, you're going to ask you to either put 1, 2, 3, or so forth, okay? So that's multiplicity. Now we also need to talk about, so multiplicity is the number of times a given factor appears in a factored form. So it could appear 1, 2, or 3 times like we did for this example. Okay, but the multiplicity also tells the behavior at the 0, so at the x-intercepts. So if we look at this example, we wrote down what our zeros are. So we have one at negative 1, 2, and 6. So here you could see these, one at -1, 2, and 6. Okay, and if we talk about the multiplicity, this for a -1 we had a multiplicity of 1. This had a multiplicity of 2, and here we had a multiplicity of 3. Okay, so we're discovering how does the multiplicity affect the behavior of your graph. Okay, so first off, you should notice that when we have odd multiplicity, the graph goes through the x-intercepts. Okay, and when that happens, we call it cross. So both of these cross the x-axis. And if it's an even multiplicity, it bounces, or we'll call it bounce. Okay, so it hits that x-axis and then it goes back the opposite direction. Okay, and that will happen for any of these multiplicities. So any even degree or even multiplicity, we're always going to have a bounce. And if it's an odd multiplicity or degree for the factor, it would cross. Okay, so here's an example over here on at the bottom. Are these going to cross or bounce? So here we've got x to the 1001. So since that's odd, the degree is odd, this is going to cross. Okay, we don't know what the graph is going to look like besides that so far, but at least we know that it's going to go through that x-axis. And then for this other example, this one's going to bounce because it's an even degree. Okay, another thing that we could talk about is if we look at this, I kind of wrote this out already. So if it's a multiplicity of 1, that's a linear factor. So if we look at -1, if we kind of zoom into that, that looks like almost like a straight line. Let me get rid of that other stuff, okay? It's a linear factor. It's going to act like a line at that point, okay? Another thing, if we look at the second one, that is a quadratic factor. So if we go over at that point, at 2, if we were to zoom in enough, okay, it would look like a parabola, especially when you get really close, right? The closer you get into it, it looks more like a parabola, okay? And then I think our last one, multiplicity of 3, that's like a cubic term. If you were to zoom that in, that's the shape of a cubic function, okay? Kind of goes up, crosses, and then keeps going up, okay? So that's something else you can be aware of. So like here's another example. If we extended that, if it's a degree of 4, that's called quartic. It would still behave kind of like a quadratic. It just gets a little more flat. And the same with the quintic factor, a degree of 5. It acts a lot more like the cubic. It just gets a more like wide, okay? Anyway, so that's multiplicity. The last thing is turning points. So if we look at graphs, like all of these of graphs, a turning point, like when we did quadratics, a turning point is like where the vertex is at when we talk about quadratics, okay? So we're going to kind of look at some of these examples and figure out how do we come up with turning points. So if we have a linear equation, it's just a straight line, so it has 0, I probably should write this, 0 turns. Okay, it doesn't change at all. Quadratics have 1 turn. Okay, a degree of 2 gives you a 1 turn. Okay, if it's a cubic, that's a degree of 3. Then we can have up to 2 turns. Turning points, I guess I should keep saying turning points. If we have a 4th degree, we could end up getting 3 turning points, And if we keep going, again, we're probably seeing this pattern, is that the maximum number of turns is always going to be one less of your degree, okay? So you just take your degree, subtract 1, and that gives us the number of potential turning points. You could have less. So like if you were to graph x to the third, it would be really, it would look something like that, and it wouldn't ever end up turning. So it really kind of just depends on your equation and some of the other terms of the equation. But here we're just focusing on the maximum possible turning points, okay? Okay, all right, so let's see if we can answer some of these questions now. You're going to see problems that are in standard form, you're going to see them in factored form, and you're also going to see it from a graph. So let's kind of go through all of these. Standard form, I think, is the easiest so far. We're not going to get into like finding the x-intercepts, so but we'll get into that later. But here we're just going to focus on these few topics, okay? So first off, leading term. Again, it's always going to be your highest exponent, your term with your highest exponent, so negative 3x to the sixth. The degree is your highest exponent. The leading coefficient would be negative 3. Number of roots, again, the roots based off of the fundamental theorem of algebra, that if we have a degree of 6, then we should have 6 roots, okay? And then the max number of turning points, again, it's always going to be the degree minus 1, so this would be 5. Okay, let's try another in standard form. And watch out, this one's not in standard. So we'd want to at least be aware of that so that we can find what the leading term is. So the leading term here would be 5x to the fifth. Degree is 5. The leading coefficient is 5. The number of roots is 5. And then the max number of turning points would be 5 minus 1, which would be 4. Okay. Also, feel free to pause anytime and try one of them, the examples on your own to make sure you're getting it okay. All right, so now let's do it from factored / intercept form. So this is intercept form. It gives you your x-intercepts really easily. This is also called factored form because if you factor something, it puts it into factors. So these are factors. Okay. All right, so let's see if we can come up with the leading term. So leading term, you can only find that by looking at standard form. And this is not standard form, so we need to do a little bit of work. The nice thing is that you do not have to multiply, distribute it all the way out. We only need to know what the leading term is. So we just want to focus on the leading terms for each factor. Okay? So we would want to multiply x from here, and then another x, and then we need to multiply it by x to the third. Okay? So watch out for the exponents because the x is also being cubed. And we learned in the past that when we multiply variables, we can add their exponents. So this would be our leading term. It just so happens to be just a variable with an exponent. You could also have coefficients, okay? All right, so our degree would be 5. I guess this does have a coefficient. It would be a coefficient of 1. Okay, number of roots. So it's just the degree. Tells us the number of roots. Again, those roots could be real. They could be complex. So again, I would mention this in like the starter, is that all x-intercepts are roots, but not all roots are x-intercepts, because some of your roots could be complex, and that's when like with quadratics, it's where the parabola doesn't cross the x-axis, right? Okay. All right. Roots and multiplicity. Okay, so maybe we want to come back here and we want to write down our roots. Again, the things that make it equal to 0. Again, we can set each of the factors equal to 0, and we can solve them. Some of these are probably a lot easier than others. So this one is already done. We'd have to add 4 to both sides, and we'd get x equals 4 and x equals 2. Okay, so 0, 4, and 2. I'm just going to write those down. 0, 4, and 2. All right, now we need to write down the multiplicities. So if we come and look at this, this would be for the first factor would be 1. When the 0 is for our, I don't know, I'm saying too much words. For this one, we'd have a multiplicity of 1, and for the last would be a multiplicity of 3. So it would be 1, 1, and 3. And then the end behavior, again, we talked about how if the multiplicity is odd or the degree is odd, then we're going to cross. So all of these cross the x-axis and continue on. Max number of turning points, again, is just the degree minus 1, so it would get 4. All right, let's try one more in factored form, intercept form. So again, the leading term, we want to multiply all of these leading terms for each factor. So we'd have 2 times x squared, don't forget the squared, times x times 5x. We get 10x to the 4th, so our degree is 4. Our leading coefficient's 10. Number of roots would be 4. The roots and multiplicity. So the roots, again, we kind of could do the zero product property. I'm just going to write those down. You could probably figure that out. These ones aren't too bad. So we'd get -3 would be one of them. We'd have a 6. And then this one, again, might be a little more difficult. I'm going to write that out one more time. And we would solve. So we'd add 3. And then we'd want to divide by 5. So 3/5. Okay, multiplicity. Again, we're just looking at those exponents. So we'd have a multiplicity of 2, then 1, and 1. If the multiplicity or the degree for each factor is even, then it's going to bounce, and then cross, and cross. And then the max number of turning points would be 4 minus 1, which is 3. All right, so if you have questions on that, we're going to do, in just a minute, do another example of the leading term. I feel like that's probably the hardest part, and a lot of the information is based off of that. So please make sure you spend a little bit of time on making sure you get that, okay? We kind of talk about this later on, but I'm going to hurry and do this quick. So turning points, 1, 2, 3, 4. And then we know that the degree has to be 1 more than that, which is 5, because we know that the turning points is the degree minus 1. So degree minus 1 gives us the turning points, which we found by just looking at the graph. And then we'd have to add 1 to both sides to figure out the degree. So that gives us the 5. Okay, so here's another example. I think would end up having 3 turning points, and the least possible degree would be 4. We say least because it could have more. We just know that it has to at least be 4 if we have 3 turning points. All right, so you're going to see something similar to this on your homework. I already did 2 of them. If you want to have a look at them, I have them on the filled-in notes as well. Okay, so I know it's a lot of information to kind of come up with, but do your best and let me know if you have any questions, okay? So first off, we want to find the leading term. So again, we want to multiply these. So negative x times x times x would give us negative x to the third. Degree would be 3. The number of roots would be 3. So those are the same. They should always be equal. The max number of turning points is 3 minus 1, so 2. Zeros, again, this one's a little tricky. People forget this one. Again, we can set each of these, all three of these, equal to 0 and solve. So we should end up getting 0, 7, and negative 4. Multiplicity, again, none of these have exponents. There would be an exponent of 1, so multiplicity of 1. And then cross or bounce, all of these would cross. Okay. All right, let's try another. Again, we're trying to find the leading term. So x times x squared times 2x. X times x squared times 2x. Okay, again, where those are just coming from these three factors. Multiply all of those. We should end up getting 2x to the fourth. So a degree of 4, and number of roots would be 4. Max number of turning points would be 3. And then let's write down these zeros. Again, zeros are the same as like your roots or solutions. Okay. And for these cases, they're also like where your x-intercepts are at. Okay, so we'd have one at 0. Because if we set this to 0, we would be equal to 0. We set this equal to 0, we'd get negative 3. Set this equal to 0, and you solve. Should probably add that, and you solve. We get negative 1/2. Multiplicities, we get 1, 2, and then 1. And then it's going to cross, bounce, cross. Okay, all right, I wanted to go over one more example because this is going to be a lot like what you're going to see on your homework, where maybe we have a little bit higher exponents. Okay, so finding the leading term, again, this is a factor. I'm going to do a different color. So we're going to write that down. Okay, again, we always just want the leading, so this would be times x squared. And this would be times 2x to the third. Okay, so sometimes people will forget to put the parenthesis. It's important that we are cubing the 2 and the x, so that would be 8x to the third. Okay, and now we can multiply and simplify. So negative 2 times 8 would give us negative 16, and then x squared times x squared times x to the third. Again, we add those exponents, we get x to the 7th. Okay, so that would be our leading term, and then we could write down some of this other information. So our roots, again, from the first factor, we'd get a 0. Our second factor, we would get 3, and our last factor, we would get 1/2. Multiplicity, looks like we've got multiplicity of 2, 2, and 3. That was a bad 3. And then behavior at those points, it would be bounce, bounce, cross. Okay, and we'll talk more about graphing these in the future, what this will look like. But suffice to say, hopefully, I don't know what I'm trying to say here. Hopefully that makes sense. All right, please stop by if you don't, if it doesn't, okay? All right, last thing, I know this is kind of long. Let's see if we can answer these questions from a graph. So the y-intercept would be negative 1, 0, just by looking. Our x-intercepts, we've got 4 of those. So we'd have one at negative 4, 0, negative 1, 0, 2, 0, and 4, 0. and then their multiplicities. So how would you know if it's a multiplicity of 1 or 2 or 3? Again, if it's even, it's got to bounce. So none of these are bouncing. And then if it was like, if the multiplicity was 3 or 5, it would be more like this, if you can see that. Okay, it's going to kind of curve a little bit and then start going back up. So if it basically straightly goes through these points, that would basically be, it would be a multiplicity of 1. So all of these have the same multiplicity of 1. Okay? And the number of real roots, well, those are your x-intercepts. So we have 4 of those. And then let's talk about complex roots. What you should expect, okay? So again, complex roots is if the turning point faces away from the x-axis. So like looking at this, we have 3 turning points, if you can see those, here, here, and here. Okay, that means that we should have a degree of at least 4. And if we look at this, we only have 2 x-intercepts. So we have 2 x-intercepts. That means the other 2 have to be complex, right? Or I guess we could have multiplicity. But I think for this example, there wouldn't be, okay? So if your turning point is kind of facing away, then we would end up having 2 complex roots. Here, let's look at another example. Well, I'll get back to that in a little bit. Okay, so this one has no complex roots because all of these turning points are facing the x-axis. Okay. All right. Number of turning points here is 3, and the least degree again is always going to be 1 more than that, so 4. Okay. All right. One more example. This has a y-intercept of -1, 0. Nope. 0, -1. I didn't mess that up on the other one, did I? I did. Sorry about that. You're probably like, Mr. Warner. Okay, x-intercepts. So here we have one at -1, 0. And just looking at it already, our multiplicity would have to be a 2 because it touches, or it could be higher, like a 4 or a 6. But I think we're just going to assume that it's a 2. Okay, it also crosses at 1, 0. That goes straight through, so that would be a multiplicity of 1. And then we have another bounce at 2. Okay, so the number of real roots, okay, there are, if you include the multiplicities, like we have 3 distinct roots, real roots. If you include the multiplicities, it would be 5. Not distinct, if that makes sense. Okay, and then complex roots, again, if it's facing the wrong direction, okay, and that doesn't include like where it touches. So that doesn't give you, I know it's facing away, but it's touching at the x-intercept. So this is facing away. That would give us 2 complex. And I think that's the only one. So we'd have 2 complex roots. If we were adding these together, that would give us 7 total roots. And then the number of turning points, again, we have 1, 2, 3, 4, 5, 6 turning points. And then we know that the least degree is just going to be 1 more than that, so 7, which makes sense because our total number of roots is the same as our least degree. Okay. All right, I know that's a lot of information. Again, please let me know if you have any questions. One thing I know this is really long. Have a look at this. This is one thing that I've had people struggle with on the homework. Again, here's a worked out example of finding the leading term. Again, sometimes people will forget the parentheses, so watch out for that If you're squaring something, it's squaring the coefficient and the variable, okay? And then also down here, if I can go back, the difference between a 0 and an x-intercept are very similar. Okay, just make sure you realize the difference. An x-intercept is an ordered pair. Okay, and if you have any other questions, please just let me know. All right, let's see if I can go back to this. Okay, thanks guys.